So today we are going to talk about central manifold. Okay, central manifold, which is very important because for systems, what if the one of the eigenvalue is zero? Then we cannot determine the stability. So if one of the eigenvalue is zero, okay, so cannot determine the stability in this case. Okay, so for example, if we have x dot is actually x square, y dot is actually minus y, so clearly 0 0 is equilibrium point, but a is actually 0 0 0 minus 1, so lambda 0 is actually 0 and lambda minus 1 is minus 1. So lambda 0 is non-hyperbolic equilibrium point. So this means that we cannot determine the stability. Then what if we cannot determine the stability of the system? Then actually what we are going to do is actually what we call it central manifold. But before going into that, so if we see the phase portrait of the system x dot is equal to x square, y dot is equal to minus y, we can have some idea. Okay, so now on x-axis, y is 0. Okay, so this means that if my x is positive, my x dot is increasing, and also my y, and if I see the equation y dot is actually minus y. If my y is positive, my y dot is decreasing, and if my y is negative, my y dot is increasing. So we can see the pattern that okay, from here, okay, so over here my solution is moving there, and over here my solution is moving there, and over here my solution approaches to 0. From here my solution also approaches to 0, but when it approaches to 0 in the second and fourth quadrant, then it starts moving away from the origin in the first and fourth quadrant for the said system. Okay, that is actually phase portrait. But now because the lambda naught was 0, so we actually did not determine the stability, that okay, whether my system is unstable or stable, although the phase portrait is telling us that it is unstable. But what, for some systems you cannot even sketch the phase portrait very easy like by hand, so definitely we need a method. So the method is actually, we are going to discuss that by an example. Okay, so example is my x dot is actually x square y minus x to the power 5, and my y dot is minus y plus x square. So now clearly lambda naught is actually 0, lambda minus 1 is minus 1, so we cannot determine the stability. So the first thing is, first we need to look at the system. Is the linear part of the system is uncoupled or coupled? Clearly in this case the linear part is uncoupled. Okay, so the linear part is uncoupled. Okay, because there is no linear term, but over here we have just only one linear term, which is minus y. So clearly the linear part of x dot y dot is uncoupled. So if in uncoupled, we will just go ahead straight away, we will say that let y is actually h of x. Why we are assuming y? Because if we see the equation y dot, we have a clear clue that okay, the linear part of the y is -1, which is stable. Okay, so that's why the variable which is stable, we will define that variable, okay, is h of x, the function of x. Okay, but h of x is what? Ax square plus bx cube plus up to so on. Why we are starting from x square? Because if we start from x, it is not going to help us, it is not going to tell us the stability. It is also definitely we will start from the non-linear part. So now we will take the derivative of y, because y is a function of t, so by chain rule we have h prime of x and x dot, but y dot is defined minus y plus x square, and h of x is 2ax plus 3bx square plus up to so on, and x dot you can put the value. We will solve for the coefficients of a, b and c. If we get one coefficient, we are done, we don't need to worry about other coefficients. So in this case, it is very easy to see that a is actually 1. If my a is 1, what is then? This implies that my y is x square. So if my y is x square, because I am interested in the x equation, so what will be my x equation? So it will be x square and then x square plus up to so on, because b, c we did not find, and minus x to the 5. So we can clearly see that that is x to the power 4 plus order of x to the 5 higher terms. Now we can clearly see that if we just see the x equation, clearly x is equal to 0 is unstable. Okay, and you will say why? If this is my 0, if my x is positive, my x dot is increasing. If my x is negative, again negative value to the power 4 is positive, so x dot is again increasing, so it is unstable. So if this is unstable, it is telling us that okay, my system is unstable. Okay, my original system is unstable. So original system is unstable. Did you see that? Okay, now it gave us a clue that okay, my original system is unstable. Now to further verify it, we can actually have the phase portrait. Okay, so we can have the phase portrait. So you saw that we saw that when we solved, y is actually h of x ax square plus b something. So we eventually end up that a was 1, so y is equal to x square. So we can actually plot that y is equal to x square over here. Okay, and then we saw that okay, because this was x dot is equal to x to the power 4th. Okay, so we saw that x dot, since x dot is x to the power 4, so we saw that if my x is positive, x dot is increasing. If my x is negative, again x dot is increasing. So increasing. Now but if we see the y dot equation, and y dot is minus y plus x to the power square or whatever. So on y axis, x is 0. So if my x is 0, y dot is equal to minus y, and if y is positive, my y dot is decreasing. Okay, and if my y is positive negative, my y dot is positive, so it is increasing. Now clearly we can see that okay, so that solution behave like this. Okay, that it is moving away from the origin, and also when it approaches here, it is moving that way. From here definitely it is approaching 0, it is approaching 0, but as it gets to 0, then it starts moving away from the origin. So clearly we can see that this 0 is unstable. Okay, so if we see the another example, okay, so then we assume that, okay, so for the another example we assume we consider different examples. So you have a test that x dot is nothing but xy plus x cube, y dot is minus y minus 2x square. Again clearly a is actually 0 0 0 minus 1. So lambda naught is actually 0, lambda minus 1 is minus 1, and clearly we say that the linear part is uncoupled. And for the y dot we can see that the linear part is negative, so it is stable. So we will say that y is actually h of x, which is ax squared plus bx cubed plus up to so on. So when we will have y dot is nothing but h prime and x dot, so then we will end up with within a value of a, which is a is equal to minus 2. So if my a is minus 2, my y becomes minus 2x square, minus 2x square plus order of x cube. So then my x dot is x and y is minus 2x square plus x cube. Okay, so what is this? So minus 3x square minus 3x cube minus 2x cube plus x cube is minus x cube plus order of x to the power 4. So in this case clearly x is equal to 0 is stable. Why? Because if this is my 0, when my x is positive, my x dot is negative. Okay, my x dot is negative, so decreasing. And if my x is negative, my x dot is positive, so increasing. Clearly stable. We can see that solution is moving from both sides towards 0. But what about the phase portrait for this system? That okay, the system is actually the solution is stable. So again, since y was nothing but this was minus 2x square, so this is something, the equation is this thing. Okay, so when x was positive, we saw that my equation for x dot was minus x cube. So this means that when my x was positive, my solution was decreasing, and when my x was negative, my solution was increasing. And also y dot is actually minus y plus, okay, so minus y minus 2x square. So at x is equal to on y axis x is equal to 0. So if my y is positive, my y dot is decreasing, and if my y is negative, my y dot is positive. So we can clearly see the solution is actually approaching to 0 from every direction. Okay, from every direction. And over here, so over here if something is going up, so it will come and then it will, because always the solution will follow the stable manifold process. Okay, so again, and then it will, so it cannot directly come, and then it will go away, and also this will join and then it will go. So it always, the solution will follow the stable manifold to get to the solution. So that's where we can see that every solution is moving towards the origin, so stable. Okay, So that's what actually the center manifold. Center manifold is actually when we have eigen non-hyperbolic video, then we have to first linearize the first uncoupled linear rise part of the system, and then we have to actually find the constant, and then it will tell us okay if my system is unstable or stable. Okay, that's it from my side.